everyone. In this video lecture, we will learn how to implement basic logic gate using universal logic gates. So let's start our implementation using first NAND universal logic gate, in which first we will see how to implement NOT gate using NAND gate. So as you all know, the expression of NOT gate is nothing but when we will provide a NOT gate input as A, then the output will be NOT gate will be A bar. So we will get the complement of input in NOT gate, and parallelly we will write a NAND gate expression also. So this is the NAND gate when we will give A and B as two input to the NAND gate, then we will get A into B whole bar. Now we will compare these both expression and we will try to get this NAND gate expression as NOT gate expression. Then we can say we we are able to implement the NOT gate using NAND gate. Okay. So from this expression, we need to think like how we can get the A complement, that is the output of NOT gate. Okay, so let's see. As you all know, A into A is equal to A. So this is the basic fundamental that we need to keep in our mind during the implementation using NAND, NOR, even using MUX also. So by observing this expression, we have seen here A into V whole bar. I need only A as mentioned in the NOT gate expression. So if I will replace this V with A, then I can say like A into A is equal to A. And if there is one complement also, then this complement remains same and it will be A bar. So what I have changed here? Nothing but just I have replaced this A with V. So from here we can say if we will connect the NAND input, both input with A, then we will get the output expression as A complement, means the NOT gate output. Okay. So like that, we have implemented the NOT gate using NAND universal logic gate. If we will rewrite this representation, then we can also take one common input and connect this common input to the both leg of the NAND input, and we will get here the output as NOT gate. Okay. So we have successfully implemented the NOT gate using NAND gate. Now let's see the next another gate implementation using NAND gate. So we will implement next the OR gate. So first we will write the OR gate equation. As you all know, the OR gate equation will be when the A and V will be the output, then the output expression of OR gate is equal to A into A plus B. Sorry. And parallelly we will write the NAND gate expression as well. So NAND gate expression is A to B whole bar. Okay. So now our job will be to get this expression from this expression. Okay. After that only we can say we have implemented the OR gate using NAND gate. So first we will observe this and try to get the OR gate expression from this expression. Okay. So there is one method, or we can say one theorem, De Morgan's method. So that says if there is the whole complement of two or more variable, then we can expand this in OR A bar plus B bar, like that. So this is nothing but this is the De Morgan's theorem that also you need to keep in your mind during the NAND gate implementation. So from this expression, we will observe one thing. We get the OR expression here, but the problem is this A bar and B bar. So if we will remove this bar from this A and V variable, then we will get A plus V. That all we want. to get the OR expression. Okay. So what if I will say, if I will uh, provide a complement input to the NAND gate, then we can say like we will get this kind of expression after applying the De Morgan's theorem. Okay. So like that. And you all know whenever there is double complement in any variable, then this complement get cancelled and we will get the variable without any complement. Okay. So we will get from this expression A plus B, simple. Okay. Just now only we have seen the NOT gate implementation using NAND gate. So we will use that concept here and we will provide the complemented input to the NAND gate to get the OR gate as we have discussed here. So what we will do, we will just complement the input using the NAND gate implementation. Okay, that we have discussed now. So we will connect these to the NAND gate and here we will what we will get A complement and V complement. Okay, so that we will connect to our NAND gate and we will get the final output expression as A plus B, that all we want here. So how we will get here, that just now we have discussed, like A into B complement and whole complement. So this will expand using the De Morgan's theorem, so that double complement will cancel and that will come as A plus B. So that's all. That's how we can implement the OR gate using NAND gate. Now our the last gate is remain from the basic logic gate to implement using NAND gate, that is AND gate. So that will be our third AND gate. As we all know, NAND gate is nothing but it is a complement of AND gate. Okay. So from that concept, we will implement the AND gate using NAND gate. So this is the expression of NAND gate. Okay. A into V OR. If I will complement this expression again, then I will get the A into B. That is nothing but it is a expression of AND gate. Okay, that is all we want here, so that we can say we have implemented the AND gate using NAND gate. So what we need to do here, just we need to connect this output with our NOT gate and we will get the or NAND gate. Sorry. So we have seen in last implementation how to uh, get the NOT gate using NAND gate. So with that concept, we will connect this output expression further to one more NAND gate, and here what we will get, the output expression as AND gate. So like that we have implemented the AND gate using NAND gate. We have seen here the basic 3 gate implementation using NAND gate. Now we will see the NOR gate implementation. Now let's see the implementation using NOR universal logic gate. Here also we will first implement the NOT gate using NOR universal logic gate. So for that first we will draw the NOT gate expression. So it is the complement of its input, and parallelly we will write the NOR gate expression so that we get the clarity on the both expression. So this is the expression of NOR universal logic gate. So similarly, as we have seen in the NAND gate implementation, here also we will try to do something in this expression, NOR gate expression, so that we will get the NOT gate expression. Okay. So here is also one fundamental, like we have seen in the NAND gate implementation, A into A is equal to A. So here we will see one basic fundamental of digital design, that is A plus A will be A. Okay. So in this expression, if I will replace this V with A, then can I get A plus A from here? A plus A is equal to A, and this complement will remain same. So we will get final A bar. Okay. So this is all about the NOT gate implementation using NOR gate. Here we have got the NOT gate expression. We can rewrite this, that we will connect these both input of NOR gate to a common input, so that NOR gate will treat like a NOT gate. Okay. So this is a NOT gate using the NOR gate implementation. Okay. Now let's implement our next logic gate with the NOR universal logic gate. So we will implement here the AND logic gate using NOR universal logic gate. For that, just write the AND gate expression as well as NOR gate expression. So it is the expression of AND gate, and also we will write the NOR gate expression, that is A plus B whole complement. So our job will be to change something in this expression so that we will get this expression. After that, we can say we have implemented the AND gate using NOR gate. For that also, we have seen one mm, method or one theorem, De Morgan's theorem, that says if we will uh, expand this, then we will get the A into B complement. Okay. So here, what I have seen, like we have got this A into V, but there is one complement, and V also there is one complement. If we will able to remove this complement, then we will get A into V. That is all we want. Okay. So what if I will give a complement input to a NOR gate, then we can get what we are expecting, like A into V whole complement, and that will be convert to a double complement, and this double complement will cancel out, and we will get this A into B. Okay. So we have seen here, if we will connect our NOR gate input as a complement input, then we will get this expression. Just now we have seen here how to treat our NOR gate as a NOT gate. So that concept we will use here, and we will get the AND gate using NOR gate. Okay. So let's say that NOR, for this complement, we will connect one NOR gate to A input and second NOR gate to the B input. Here we will get A complement and B complement. Okay. And that complement we will connect further to a NOR gate to get a final expression as AND gate. So that will come A in A plus B, and that will become whole bar, and that will cancel out, and we will get the A into B. So that is all about the AND gate implementation using NOR gate. Okay. So now let's see our last basic gate implementation using NOR gate, that is OR gate. Okay. So as we all know, NOR gate is nothing but it is a complement of OR gate. Okay. So just if we will complement the OR gate out, NOR gate output, sorry, then we will get the OR gate, means this is the expression or output of NOR gate A plus B whole bar, and this is the output expression of OR gate A plus B. Okay. So anyway, if we are able to convert or complement this final output, then we will get this OR gate output. Okay. So what we will we need to do, just we need to connect this output to a NOT gate to get the OR gate expression. Okay. So we have seen here in the last implementation how to treat a NOR gate as a NOT gate. So from that concept we will get the OR gate expression. So here we will get A plus B complement, and that will come again to a NOT gate, and that will cancel out, and we will get a final expression as OR gate. From this video we have learned how to implement the basic logic gates using universal logic gate, and in upcoming video we will implement the large equation logic expression using only NAND universal logic gate or using only NOR universal logic gate. So stay connected. Just remember the basic fundamental how to implement any logic gate using universal, either it can be NAND or NOR universal logic gate. So we have seen, like, just we need to remember this fundamental: A into A is equal to A plus A is equal to A, and one De Morgan's theorem that will say if we will convert this and expand this, that will come A plus A bar plus B bar, and again vice versa. Like if we will see this kind of expression, then we can convert this into A into A bar into V bar. Okay. So these are some basic fundamental that we need to keep in our mind during the implementation using only NAND or using only NOR. So stay connected for the upcoming video. Thank you everyone for watching with this video till end.